Embedded devices have an increasing presence in our daily lives. It is expected there will be 50 billion embedded systems connected by 2020. During their operation, embedded systems are often required to store, access, or communicate data of sensitive nature, making security a serious concern. Additionally, security is cited as the single largest concern among surveys of prospective commercial users. In the past, attacks on cryptographic implementations inside security embedded chips goes back as far as 2001s, and prospects of practical feasibility to attack and exploit networked embedded devices dates back to 2002. Researchers Researchers explored large botnets based on embedded devices in 2007, and the first malware targeting embedded devices that constructed a full-fledged botnet was discovered in 2009. The extent and implications of default usage in embedded devices have been studied at large since 2010. In the present, the scientific community and vendors needed a decade to start reacting to the numerous wake-up calls related to attacks and vulnerabilities. There are currently many instances of large-scale or impacting vulnerabilities and attacks that could have been checked, fixed, or prevented years ago. So, key takeaways to take are the problems, vulnerabilities, and attacks and exploits that endanger the security and privacy of embedded devices in the short, medium, and future term may have been explored already. However, finding the relevant and applicable research has proven to be strenuous. Thus, key takeaways could be summarized as the attacks and defenses of embedded devices may have been identified as now laying a solid foundation for research. So, for power consumption optimization, expenditure represents the most challenging design factor of the development of security schemes in battery-powered embedded systems. This factor can directly affect the overall system's lifetime, such as the sensors where replenishment of batteries is not possible. However, conventional security mechanisms tend to be conservative in the security guarantees, adding a large number of message overhead and computation, which induces high energy consumption. Potlapalli et al. In his research shows that the introduction of encryption in networked sensors communication may decrease the battery life by a factor of 80% due to the use of cryptographic primitives implies additional complex computations for the embedded systems processor during the key setup and data decryption phases. To face this challenge, energy sufficient security protocol execution is highly required. So, for addressing power limitations issues in embedded systems can be done by enhancing the hardware capability of the embedded systems or reducing the energy consumption of security mechanisms. On the supply side, and beyond the improvement of batteries capacity whose growth doesn't exceed 8% per year, architectural solutions described in the previous section are of great importance. They considerably reduce the energy dissipated by security processing through the optimization achieved in the execution workload and the use of energy sufficient hardware operations. Adversely, adapting the existing security mechanisms to the energy constrained environments and embedded systems or proposing new energy efficient approaches is paramount. We represent energy efficient security mechanisms in embedded systems regarding to two functional levels. The first considers the primitive levels of protocols building blocks, minimizing energy expenditure, and this level mainly consists in carefully choosing the employed algorithms and adequately adjusting their tuning parameters and operation modes. So a solution would be energy efficient cryptographic primitives. In the symmetric encryption, their algorithms can be either stream or block ciphers. In the former class, the plaintext is encrypted in one bit at a time. This class is appropriate for applications where buffering is limited, or when characters must be individually processed as received. Since most stream ciphers used in practice tend to be proprietary and confidential, relatively few fully specified algorithms exist in the open literature. One of the well-known ciphers is RC4. By contrast to the first class, block ciphers tend to simultaneously encrypt fixed-size blocks of the plain text message using a fixed encryption transformation. Examples of block ciphers include the 3DES, AES, and the blow phase techniques. For the encryption-decryption operations, both stream and block ciphers use one input secret key, which is expanded during a key setup phase in order to derive a distinct and cryptographically strong key for each round. A round denotes a repeated sequence of mathematical computations that form the overall cipher's algorithm. If we consider the overall cipher's functioning, that include both key setup and plaintext encryption decryption phases, AES appears as a judicious choice because of the competitive energy costs. Moreover, AES cryptanalytic properties have been well studied, allowing it to combine energy efficiency with acceptable security level. Another way is energy efficient security protocols. Security protocols allow several embedded systems to communicate in a secure manner with guarantee of baseline security goals such as sensitive data, confidentiality, or entity authentication, depending on the system's nature and their corresponding applications. Several security protocols have been developed, although that some of these protocols are tunable and can be adaptively executed to optimize their energy dissipation. Rare are those that considered energy efficiency as an early design objective. Adversely, several works have been conducted to explore the possibility of adapting conventional security protocols, initially proposed of wire networks, by altering their behavior for embedded devices so that an acceptable trade-off can be achieved between the security level and corresponding energy requirements. Another example from Potlipelli presented a comprehensive analysis of the energy consumption for the transport layer security protocol SSL on IPAC PDAs. They studied the impact of various functional parameters like adopted cipher suites, key length, and data transaction size on both processing and communication stages of protocol. Moreover, the effects on some optional operational modes like mutual authentication enabling on the overall energy consumption of SSL have been emphasized. Based on the study, authors concluded that there exist several opportunities for energy saving in SSL. These opportunities mainly emerge from the operating flexibility provided by SSL, the availability of various parameters in cryptographic algorithms like key size and number of rounds that can be tuned to attain the best trade-off between the security level and energy consumption, remarking that the proposed optimization techniques like adaptive session negotiations and certificate size reduction highly depend on the protocol's functioning and do not apply for all security protocols. Consequently, it is important to investigate the development of protocol-level generic optimization methods that can be integrated in every security protocol to enhance its energy consumption. So, for that, the dynamic voltage scaling technique is used to allow embedded processors to operate at an energy efficient manner by dynamically adapting voltage and therefore clock frequency for data encryption, decryption, and processing phases. We have seen that in class. Based on that assumption, the energy requirement for encryption, decryption, and asymmetric ciphers is not proportional to the message length. Authors presume that the introduction of additional header in the transmitted message enhance the energy expenditure for encryption slash and decryption at the receiver. However, the energy gained at the receiver may not compensate the additional energy consumed by the sending during the added header transmission. Another point is tamper resistance. The theoretical strength of the utilized cryptographic primitives does not reflect in any case the security level for the embedded system. This later also depends on the quality of the primitives implementation, and by that we mean tamper resistance. So one of the features of tamper resistance is physical and side channel attacks. This class integrates all attacks that integrate with the embedded system's hardware and exploit the physical side physical side of system implementation flaws and properties. Invasive attacks like micro-probing techniques that generally require getting access from the chip level components in order to interfere and manipulate with the system internals. Concerning side channel attacks, several prevention software and hardware approaches have been proposed to mitigate symptoms that allow the leak of the system's side channel information like power dissipation, timing, electromagnetic radiation. On the hardware level, randomization can also be applied on the clock signal or the power consumption. Moreover, aggressive shielding techniques as well as methods that break the locality of chip layout are effective in defeating electromagnetic analysis attacks. Although it has been shown that software-based countermeasures are versatile and most efficient, they considerably hinder performance and cryptographic algorithm in terms of energy, memory, and execution time. Hence, the challenge to achieve is the development of side challenge mitigation techniques with as little cost as possible. Another type of attack is software attacks. These major threatening attacks are leveraged by the system's capability to download, upgrade, and execute application codes. They are essentially based on malicious software tools and exploit the logical side shortcomings of the embedded system's implementation. One type of attack is interception-based attacks. They try to passively eavesdropping sensitive data in order to compromise the user's privacy or the confidentiality of exchange data. An example is the use of logical analyzer for inner line bus probing of an embedded system. Another is interruption-based attacks. They target the system's availability by making it unusable. This could be done through an energy exhaustion attack that exploits the scarce energy resource in battery-powered systems and make them undergo additional workload in order to drain out their batteries. Such denial of service attacks are also privileged in low-end embedded systems with limited processing and storage capacity, where the device can rapidly fail in the case of intensive workload. Another type is modification-based attacks, and they compromise the software integrity by exploiting detected vulnerabilities. A common example is the use of buffer overflow vulnerability to override the stack memory and thereby transfer control to a malicious program whose execution can have undesirable effects. The solution to that is one approach that overcomes the processing inefficiency of the software-based solutions is to completely implement the resource-greedy cryptographic computations on a dedicated hardware using ASICs. With this manner, the embedded processor can offload the cryptographic computations through high-speed bus, for example, to the custom hardware designed to guarantee higher processing speed and lower energy consumption. Various companies offer cryptographic hardware accelerators that implement diverse asymmetric and symmetric ciphers for systems ranging from low-power mobile appliances to smart cards to high-performance network routers. Though this hardwired algorithm approach has proved its excellent performance level, it's much less effective in terms of cost and flexibility when several crypto systems are required in order to support multiple security protocols, emerging standards for better systems. In an attempt to achieve a trade-off between processing performance, flexibility, and design cost, a third-generation solutions have been proposed. They can be classified into two subcategories: processors enhancement with special purpose extensions and general purpose extensions. For special purpose extensions, this approach is denoted by application-specific instruction processors, also ASIP, consists of tightly integrating the accelerator's hardware circuitry in the processor's core itself and invoke it with special instructions. A typical type is to implement one route of symmetric cipher, such as DES, within the processor hardware and invoke it using a custom instruction. This solution allows one to guarantee enhanced performance for the intended specific cryptographic algorithm but misses flexibility. Indeed, no processing acceleration could be achieved from any other cryptographic algorithm. General purpose extensions. In order to improve better flexibility than in the previous ASIP approach, based approach, designers chose to improve the processing capability of general purpose processors with instruction set that are indeed general purpose primitives. These instructions usually execute versatile operations that potentially compose more complicated functions employed in different cryptographic algorithms or other resource greedy applications. PAX is a typical example of new reduced instruction set processors that are in, that integrate general purpose extensions to accelerate both symmetric and asymmetric cryptographic computation. This approach is promising for an embedded processors in smart cards and network sensors where flexibility is required with small form factors and low energy consumption. And the last point is cost reduction. As emphasized earlier, embedded systems are often highly cost sensitive. Since can affect the building of millions of units. Integrating top level security is not always cost effective for embedded systems as it mandates the use of more expensive hardware and software and requires a long time rigorous design process along with environmental failure, protection, and testing. Consequently, the designer's responsibility consists of balancing the security requirements of an embedded system against the cost of implementing the corresponding security measures. And this ends my presentation for my 467 project. Thank you very much.